welcome to day 5 of Unit 1. Today we're going to investigate some further properties of limits in general. And of course, just reiterating from before, that as x approaches a certain value, letter A, it says that the value becomes closer and closer to L as x gets closer and closer to A. So as we approach it from both sides, we are coming to a common value of what we think should happen. And of course, both sides must be the same value, and the function not necessarily has to be defined at that point. Right, so we don't need the function to be defined at that point. We just want to know what do we expect to get. So let's within a given function. So instead of looking at the graphs that we did the last couple days, let's look at the function itself. And what we can do here is we're going to break apart our function into individual parts. So we can think of this sort of method 1, that the limit of x approaching 3 of our function, and we have here x squared plus 2x plus 1. This, of course, is the limit of x approaching 3. And if we notice, this is actually a perfect square, so we can have it as x plus 1 squared. And if we think about that and substitute in, if we approach 3 from both sides, we will get that value of 4 squared, or indeed 16. Now we could, of course, method 2, think of it just as it's written to us. So the limit of x approaching 3 of this value of x squared plus 2x plus 1, we can think of it as individual parts. And so really what we're dealing with is the limit of x approaching 3 of x squared, and then we're going to add to that the limit of x approaching 3 of 2x, and add to that the limit of x approaching 3 of the value of 1. So we're thinking of it as sort of broken apart into individual functions. And what's going to happen, of course, is of our x squared, we will indeed, thinking of the graph, thinking of table of values, we will end up with 3 squared here. With our nice linear line, we will end up with 2 times the value of 3. And of course, limit of x approaching 3 of 1. 1's always going to be 1, so it's still left there. So we have 9 plus 6 plus 1 are also 16. So we can actually break this apart into individual parts, and it still gives us the value of 16. What happens, of course, is that in this polynomial case, it actually works that direct substitution into either form will give us a result of 16, which we want, and which is the answer. So, which brings up what we really have. Well, here are 7 general properties of limits that will always be true. The limit of any constant is that constant itself. That's sort of hopefully self-explanatory. The limit of the value of x as x approaches a will be a itself. So a linear line will always come in there. If we add or subtract functions from each other, these are of course polynomial functions, and both having limits, we again of course can break that apart and do its individual parts, which we did in the second method 2 of the example we just did. We can of course have any constant times that multiple. So this is sort of in the middle, that 2x part. We could have the limit of x and then just multiply the value by 2 and we're done. X squared, this is sort of a function time a function. of course, we can break it apart into its individuals as well as division, of course. And look at that, we have our power of n, which is sort of our method 1, where it was squared. We could have our 4 and then square it afterwards. So all these 7 properties will always exist, and they're sort of our general guiding principles into any general function of limits as we go from here on. So let's try a bunch using those properties, and remember, of course, that we want it to be defined. So for any polynomial function, the limit will exist, and we can do direct substitution. That makes it nice and easy for us, and we always want that to be true. So it's lovely if we have our polynomial functions. We just direct substitute in, and we have our final answer. However, sometimes direct substitution doesn't work. One of these, of course, is when we end up with the form 0 divided by 0. That we like, actually, because when we have 0 divided by 0, we can do several other things to our functions, algebraically, that is, and we'll end up, hopefully, getting rid of our 0 divided by 0, and then direct substitution will work. So we go from there. So let's take a look and see what we can do with some of those. So, not a polynomial function, we have its actual rational function, but however, of course, let's always try direct substitution first, because if we direct substitute in, even knowing we can cancel here, we don't need to, because we don't have division by 0. So we're okay. So we're going to end up with 5 in the numerator, 5 squared being 25 minus 25. We're going to end up with 0 in the numerator, but in the denominator we still have 10, and of course anything divided by 0 is still 0. So our limit actually works with direct substitution. In our second case, part B, this doesn't happen. When we direct substitute into our denominator, we get 0, can't divide by 0, so something else must go. So what do? Well, we actually break apart that numerator. So we're going to limit of x approaching negative 5, and what we're going to do is we're going to break that numerator into its 2 parts of x plus 5 and x minus 5 over x plus 5, and that, of course, makes it, of course, that those things will cancel, and we're left with here. So, as I was saying, what we're left with here is the limit of x approaching negative 5 of the function x minus 5. Right? Remember, of course, x cannot equal negative 5, but direct substitution does work, and we end up with negative 5 minus another 5, or negative 10. So the limit exists even knowing the function itself, remember, was not defined. And what do we do in our next case? So again, we can try direct substitution. We end up with division by 0, so we'll look for something else. We substitute in the numerator. We notice we actually we'll end up with 25 plus 25 or 50 over 0, which of course doesn't work, and so therefore this limit does not exist. We didn't get that 0 divided by 0, which we wanted in order to try to cancel stuff out like we did in part B. So whenever we have this, we try to. The giveaway here, of course, is that our numerator goes to 0, and we check our denominator. 3 squared is 9, minus 21, plus 12 gives us 0 as well. So actually our factor, we know must come out of our denominator, is that x minus 3. And of course then, so what multiplies by 3 to give us 12? Well, that would be x minus 4. And again, of course, we end up with some canceling here. And so we end up with the limit of x approaching 3 of 1 over x minus 4. And of course, now direct substitution will work. X, of course, cannot equal 3. And when we substitute in, we get 1 over 3 minus 4, or the value of negative 1. So, not too bad. We can try a direct substitution. Doesn't work, then we try something else. If we have the 0 divided by 0, Otherwise, the limit does not exist. So let's try a few more. And in all these, of course, we're just doing some algebra to try to get us to those 7 general property rules that we want to try to do our direct substitution. Here, of course, 0 divided by 0, we got nice common factors of x in both numerator and denominator. So let's factor those out. So if we take out x out of the numerator, left with 2 minus x squared. In the denominator, take out that x, we have 5x plus 1 left over. And like I said, those x's cancel. So those x's cancel, and we're left with value of the limit of x approaching 0 of 2, minus x squared over 5x plus 1. And if we substitute in there, of course, x, of course, not equaling 0. And we substitute in, we'll get to 2 over 1, or just the value of 2. So that's a nice one there. Our next one here, realizing, of course, put in negative 2, we do get 0 divided by 0. So what do we do? This one, of course, we have to remember from our functions class that we can actually factor out a binomial out of a sum of cubes, it being, of course, the cube root of each part. What we're left with is the first part squared, opposite sign, so minus first times second, so 2x, plus the second part squared, which will be, of course, in this case 4. And again, our 0 parts, so to speak, cancel out. And we're left with the limit of x approaching negative 2 of our function. Oh, it's over 1, x squared minus 2x plus 4. Of course, now direct substitution works. So substituting in, negative 2 squared will be 4. Negative 2 times negative 2 will give me also again 4 plus the last 4. Making sure, of course, x does not equal negative 2. And of course, adding that up, we end up with a value of 12. So hopefully that made a little bit of sense. And so let's scroll that up a little bit. And we're left with our last case here. How are we going to do this one? Well, remember, of course, again from our functions, that a lot of times the division by zeros, when we have radicals, we like to rationalize. So 5 plus the root of 20 plus x over 5 plus the root of 20 plus x. And up top, of course, difference of squares happens, so we'll end up with 25 minus that's 20 plus x. And on the denominator, we'll leave that 5 minus x by itself, because we don't want to multiply this out, because hopefully, of course, we will cancel out our division by zeros. And of course, if you're looking ahead into what we actually have, we indeed do have that, because we'll have 5 minus x left up on top, with that 5 minus x in the denominator, 5 minus, plus the 20 plus x also in the denominator, and again, that 0 part canceling out, leaving us with the limit of x approaching positive 5, with 1 over 5 plus the root of 20 plus x, of course x not equaling 5. And now, of course, direct substitution does indeed work. 1 over, we'll end up with 5 plus the root of 25, which is also 5, or 1 over 10 being our final answer. So when we have radicals, one thing of course to try is rationalizing if we have that division 0 divided by 0. If not, try direct substitution. So let's try one more. Oh, this is a big one. What do we notice up top? Well, what we can try to do is see if we have any common factors, and it looks like we do. Looks like we have a common factor of 2 at least going through. So we take that out. 2 times x cubed minus 5x squared minus 2x plus 10 all over x minus 5. And it almost looks like we have a factor by grouping possible here. So let's try that. So if we have 2, looking up top, we're going to take out an x squared. We're left with x minus 5, which is what I want, of course, because that's in my denominator, which I hopefully will get rid of. So minus 2. And look at that, we have an x minus 5 as well. That's really, really nice. Of course, if we didn't see that, we would of course use long division. So we have 2x minus 5 coming out, and an x squared minus 2 left over the x minus 5. Again, that canceling, leaving us with the limit of x approaching 5 of our value 2 times x squared minus 2, where x again cannot equal 5. And now, of course, direct substitution works. Putting it in there, we'll end up with 2 times 25 minus 2, which of course is 23. 23 times 2 is 46. Okay, so that's how we can do it and work through, just trying our best to substitute in, trying our algebra, factoring techniques, rationalizing, anything that we can in order to find out, try to reduce that 0 divided by 0 into something where direct substitution will work. Remembering, of course, that all polynomial functions have a division by direct substitution will work for them, that division by 0. So, again, let's try some questions. Page 45 is today's questions, and work through this. The properties of limits, remembering those 7 basic properties, are our guiding principles through the next parts.